All right, lesson 2, the stoichiometry of neutralization. So in this reaction, in this set of reactions and set of problems, we're going to really be focusing in on our friend, the concentration formula. So if it's been a while since you played with the concentration formula, this is a really important one to work with in this unit. We did a little bit in the precipitation reactions, so let's get back at it. So we're going to be looking at writing the balanced associated reactions, which we already did in the previous unit, in the previous lesson, and then we're going to substitute values into an equation above and solve for the required amount to find moles of that given amount. So this is really important that we establish that the concentration is equal to the number of moles divided by the volume. Or if you want to think about it visually, if you had a little box and it was, say, 1 liter in size, and there were 4 moles of something floating around, then it's 4 in 1 liter, or 4 molar. And this is important to keep this image in your mind, because when we do some of these experiments, we're going to be taking 2 solutions, and we're going to be combining them in many cases. So if we had 2 10 ml solutions, we might end up with 20 mils, and then that changes the concentration of the ions that are inside. We might also need to go back to our molar mass equations. So the number of moles is equal to the mass divided by the molar mass. All right, so here's an equation. Here's one that I worked out. So let's see if we can step through this. We'll try to clean up some of these little writing I've done here. All right, so we're going to calculate the concentration of hydrochloric acid if 25 milliliters, which is a volume, right, is just neutralized. So they're trying to say that it's exactly at the neutralization point by a mixture of 40 milliliters of 0.15 molar sodium hydroxide solution. All right, so that's interesting. We've been given a volume and a concentration over here. So that's going to be very useful in a second. So let's write out the equation. We have hydrochloric acid and sodium hydroxide being combined, making H2O and NaCl. So that mole ratio is 1 to 1. This is going to be very useful. That means that however many moles we get of one compound at the neutralization point, the number of moles will be equal to the other compound. So here we have a concentration. We're going to use the one we have the most information on, which is this sodium hydroxide stuff here. So this, we have lots of information here. We have 40 mole. We have the volume and the concentration, which is 2 parts out of our equation. Right, 2 out of the 3 parts of the equation. If you know 2 out of 3 things, then you can solve for the third. So I'm going to do a little rewrite of that equation in this problem. And so here's my rewrite. I reorganize it to be N is equal to C times V. This is an equivalent equation to the previous N over V is equal to C. Okay, so we're over on this side here. So I take my concentration, here's the concentration, 0.15. I take the number of moles. I'm trying to figure out the number of moles. I find out that 0.15 moles per liter times 0.4 liters. So I'm down here. This gives me a number of moles equal to 0.006. Once again, I'm looking back up to my 1-to-1 ratio, and I'm going to say, hey, if it's a 1-to-1 ratio, then that means that 0.6 moles of sodium hydroxide is equal to 0.006 moles of hydrochloric acid. And then I can calculate a new concentration by dividing by my volume of hydrochloric acid, 0.25. This is probably one where lots of students will get confused. They'll use the wrong volume. Maybe they'll use the 40 mils or they'll use something else. So try to be careful. and the result will be this. So 0.006 divided by 0.025 gives us 0.24 moles. All right. So we can make this statement here at the bottom that mixing of 25 milliliters of 0.24 molar HCl with 40 milliliters of 0.150 molar NaOH will give us a neutral solution. Essentially, you've got 65 milliliters of some sodium chloride that you made. What's the concentration of that sodium chloride? Well, that's another question we could ask. That's not a bad question to think about. So let's just see if we could do that. So if we had to do a little thought bubble here, what is this? Well, how many moles of sodium chloride do you have? That's right. So because the sodium chloride here is made from the sodium hydroxide and it's made in a 1-to-1 ratio, we have as many moles as we have sodium hydroxide moles. So the moles of NaOH have to be equal to the moles of NaCl. So we could actually figure out that this is what the concentration of salt is in this solution by taking the number of moles of NaCl and dividing it by this new solution that we made, 0.065 liters. All right, and then I need a calculator, which I don't know if I have one ready to go right now. Let's just pull this one over. So clear 0.006 divided by 0.065, and we get 0.092. And that's a molarity. So there'd be actually a really interesting set of questions here that would combine both units, where we could even have a test for now the salt produced at neutralization, does it produce a precipitate? And certainly sometimes it would, if we had the right kind of mixture. All right, perhaps I've been thinking too much about precipitates. Here's a new sort of setup you can also try. So I'm gonna I'm just gonna get my big pen here. I'm gonna do some white out here. Okay. So if we have we have 1 molar potassium hydroxide is needed to neutralize 750 mils of 0.5 molar nitric acid solution. So I write out my equation. Here's my nitric acid. Here's my potassium hydroxide, both monoprotic. So that tells me that the ratio is 1-to-1 at the point of neutralization. And that's really useful to know, 1-to-1. So then I created this little schematic here, and I'll try to guide you through what I did. All right, so I wrote my acid on one side and my base on the other, and I tried to collect the N, the C, and the V, N, the C, and the V as I went. So I made sort of a little T-chart. And so here I wrote down the things that I knew and the things I didn't know, and you can see what happened here. So I wrote down my volume of my acid, I wrote down the concentration of my acid, and then I realized that if I multiplied my volume and my concentration together, I could get N. And then I said, well, okay, so N is equal, because the ratio is 1-to-1, this thing I've squared at the top. The ratio is equal, so I can bring that N over. And I can also fill in, at my concentration level, I can also fill in the concentration of potassium hydroxide that I used. So that's where that 1 molar, and I found out that if I want, oops, that's too thick, a line there. If I want, I can take that I can determine volume by dividing the number of moles by concentration. So in a way, I've got a sort of setup here where I can multiply going up, and I can divide two numbers going down. Will it work every time? I'm not sure. I believe if this will apply as long as it's always C and V that are being multiplied, and if it's always N divided by C or divided by V. Our options for this equation are N over V equals C, N over C equals V, and N is equal to C times V. So as long as you're never doing anything that's not outside of these three equations, then maybe this little schematic chart could work for you. So good luck with that. Hopefully it helps you. All right, and let's look at one more example. So here we're going to talk about polyhydroxide and polyprotic acids. So these ones we have to now use a different ratio. So I've done the same thing. I'll show you, I'll do the same sort of cover up here. Let's see, what do we want to do? I think we want to cover this up for next. Ooh, we have to cover that up, and we have to cover this one up. Okay, so this is what I essentially did is I took my question, I wrote out my equation at the top here, and so there's my equation. I realized that the ratio is different this time. This time I have a 1-to-2 ratio. So I had to put a new line into my table. I put a ratio line that I'm going to keep right at the top of my table so I never forget it. So it's 2 acids for 1 base. And then I filled in the table as much as I could. So I filled in my concentration, I filled in my volumes that were given to me, and I went, okay, so I'm allowed to multiply concentration and volume to determine my base. So that's what I did up here. And then I looked at this ratio and I said, okay, well, if there's 2 times as much as this one, then I need to divide it by 2 to get to reduce my number of moles. So you can see that I had my result was 0.025 0 moles, and so I moved that over moles, and so I moved that over to the other side, to the base side, by dividing by 2 so I could have half as many. The ratio dictates half as much base per acid. All right, so then I just looked and I had an N and I had a V. So over here, what I'm going to do is I'm going to take my N divided by V to get my C, and we get this. We get a final concentration of 0.056, and that's it. That's the final answer. So you can see another version of this. This one I was a little bit scrappier with my writing, but the exact same idea. The red has been filled in second, so I started on the right this time. I started on this side with my base concentration and my base volume, multiplied those two, multiplied those to give me N, and then I used the mole ratio and said, again, I have 2 bases for every 1 acid, so I need to divide in half. So going this way, I divide it by 2, and I ended up with a different value, with half as many moles, and then I took my half as many moles and divided by my concentration to get my volume. One thing to think about is if the molar ratio is 1-to-2, then the concentration needs to be 1-to-2 if the volumes are the same. And so notice here in this question we had the exact same volumes, but our concentrations are exactly half because the chemical reaction dictates that the ratio between moles is halved. Okay, so I'm going to leave you to practice